Hello, this is Dr. Keith Miller, and this particular video is going to look at how we determine geologic time. And this is part of my playlist on evolution in the fossil record, and will give you the background for understanding how we can place uh, fossils into an evolutionary history of life, so we can understand their time of appearance and disappearance. So let's first look just at the oldest living things on Earth. Notice if you're thinking about the age of the Earth, obviously the Earth has to be older than the living things that are living in and on it. So what are some of the oldest living things that we know of today? Um, well, it turns out that many trees are quite old, in the thousands of years. And some individual trees are probably as old as 6,000 years. And a number of marine organisms, particularly sponges and corals, also can have very, very long lifetimes on the order of many thousands of years. And if you look at not just a single individual organism, but a whole structure of organisms, like the Great Barrier Reef, like a coral reef, that the living parts of coral reefs can be up to 20,000 or so years old. And interestingly enough, there's some trees that establish clones and spread by clones rather than uh, sexually, so that all the individuals in a clone are genetically identical and they're all connected to each other. And so, in a sense, they're a superorganism. And one of the most famous of these superorganisms is a grove of aspen trees in Colorado, which has been estimated to have been living for something like 80,000 years. So here are just some illustrations of those. There's sequoia trees up to about 3,200 years old. Bristlecone pines are probably one of the oldest um, trees in the world. They get well over 4,000 years old. Baobab trees are very hard to date. They don't have as good a tree ring record as other types of trees, but they're estimated to be up to on the order of 3,000 years old. And as I mentioned, there are ocean organisms that are even older than terrestrial organisms, and particularly corals and sponges. And here are some examples. Barrel sponges can be more than 2,000 years old. Um, Black corals or gold corals can be several thousand years old. Probably the oldest um, marine organism are glass sponges, which grow exceedingly slowly and can be as much as 11,000 years old. So these are just single organisms. So let's start at the small scale. How do we record days, months, years? Well, actually, tree ring dating is one very good way of doing that. Um, Trees that have rings, particularly those that live in seasonal climates, so that they grow rapidly in the spring, and then their growth slows down during later in the year, and then the fall they go into senescence and they stop growing, and then they don't start growing again until the following spring. So there's a sharp break in growth, and then there's rapid growth again for the next spring. And so one of those annual bands can be easily counted up. And the variation in growth ring thickness is the result of uh, weather and climatic conditions. So if it's a particularly uh, wet year, there might be a greater rate of growth. If there's a dry year or a drought, there may be very little growth. Other things can impact um, how quickly a tree grows. Whether it's temperature, it could be forest fires, any number of things. And so within a given tree, the tree rings vary in thickness. And every tree in a given region or area experiencing the same weather conditions will have a similar pattern of rings. And so within 1 year, if you have a very tree that's several thousand years old, that gives you a several thousand year record of weather and climatic conditions during the growth of that tree. But you can actually match up living trees and dead trees and extend the length of that record to over 10,000 years. So here's some examples of tree rings. Um, Again, you see the very clear demarcations. You have the large cells in the early spring. That's when growth is very fast. The trees are growing rapidly. Then as it goes into the summer, growth slows down, eventually stops in late summer or early fall. And then there's a break and the tree goes into senescence. It doesn't continue growing. And then the next spring, it starts growing again. So again, each one of those rings is 1 year, and they're going to vary in thickness from year to year. And so they can be matched up. And so here is an illustration of that. Um, so, um, so you have a living tree. You can see the tree ring record of that. And you have dead trees. And you can find places where those pattern of rings match up. And that allows you to extend the record back in time. Well, something that'll get you beyond 10,000 years or more are ice cores. And in glacial environments, particularly, we're looking at long term ice accumulation. So looking at the polar caps like Antarctica or Greenland or some other places where there's been a very long period of continuous ice cover. And snow cover, snow accumulation is seasonal. So just like those tree rings, you have accumulation of snow during the winter months. And then when the temperature warms, you can have a period where there's no snow accumulation. You might even have some melting, and you might have dust accumulation atmospheric dust that falls on the surface of that ice, and that leaves a dark line before the next snow accumulation. And in ice cores, so whether they're Antarctic or Greenland ice cores, you can drill very, very long cores that extend back as much as 400,000 years. And interestingly enough, I've mentioned this in the other playlist that I have, which deals with climate change. Those ice cores actually preserve a lot of climatic data or a lot of weather data during or preserved within the ice, within those ice core layers. So here's a picture of exposed blue ice. So this is old ice, not surface ice. This is deep ice. And you can see the annual bands within this section of glacial ice. And the cores, whether they're from Antarctica or Greenland or elsewhere, once they're drilled, they're stored and they're kept in very cold repositories. One of the largest is actually in Colorado. Um, and all these tubes are ice cores. So people can go back and look at a particular ice core, a particular section of ice core, and extract the data that they want. And the layers in these ice cores are all dated. They're dated simply by counting, but those dates can be confirmed by things like volcanic ash layers. So, as we'll see later in this talk, volcanic materials are very datable using radiometric dating methods, which I'll talk about later. So you can date that ash layer, and then you can compare it to the count of layers, and that can help confirm your dating. That's a very important thing with dating in general. That when you're actually trying to put years, dates on things, um, is that you want multiple ways of getting at the same number. If you just have one method, well, it might be good, but if you can back it up with two or more independent methods and you get the same numbers, then you're much more confident in those dates. And as I said, the ice contains a lot of information. It contains things like volcanic ash layers. It contains bubbles, air bubbles within the ice. And the air bubbles actually are captured atmospheric air from the time that that ice formed. And so you can actually look at the composition of the atmosphere over time that's preserved within these ice cores. And this is one of the main ways of reconstructing climate change during the Pleistocene, during the ice ages. Another way of getting at a high resolution um, for dating is varves. Varves are alternating layers, thin layers of sediments that accumulate again seasonally within lakes. And there's a wide range of different types of lakes, and many of those lakes produce varves of different types. Um, so you can have layers that record wet-dry climates. Um, so you get sediments washed in during the wet times, and then during the dry times, there's a little accumulation, or warm cold. Um, and you can have also in glacial lakes, you have in the spring, when the ice melts, carries all kinds of sediment that was trapped in the ice, and that gets deposited. So you get this coarse sediment load. And then after spring, after that spring melt, now the water just sits there in the lake, and then the fine materials settle out on top. So you get this kind of coarse to fine layering in glacial lakes. And one of the most famous places for recording varves, uh, and these are more of the wet, dry, warm, cold type varves, is in the Green River Formation in western US. It covers several states. It's present in several states where there were these very, very large lakes that lasted for a very, very long time. And over 5 million laminae, annual laminae, have been counted within the Green River Formation. So here's an image of the Green River Formation. Again, close up so you can see the individual annual layers in the lower right, and then look at a large cliff exposure, which would contain probably tens or hundreds of thousands of laminae within that thick exposure. Well, the things I've talked about now, uh, whether they're tree rings or ice cores or VARs, these other methods, um, can give you a high resolution picture of what's going on, but you don't actually have a date for that. So let's say the Green River Formation, if that's all you had, you can say, well, this lake represented over 5 million years of sedimentation, and this is how the climate changed or the environment changed during that time. But you couldn't say what that time was. Okay. That's a part of relative geologic time, which I'm not going to focus on in this video. Um, Relative geologic time simply determines the order of events. And that goes back to what are called the uh, stratigraphic principles of Steno and then later Hutton and some others and the fossil succession. And I talk about this in detail in another video in the playlist on evolution in the fossil record. So if you're interested in that, you can go to that video. I also have a short hands-on video that looks at a geologic cross-section and then describes how you would reconstruct the order of events. So we need something else. We need other methods to determine the actual duration of time intervals and place dates on those, place them on a timeline. Okay. Relative geologic time just says this was older than this and this was older than that. What you need is something that allows you to put dates on the timeline, be able to take what you're looking at and put it on an Earth timeline. And that's called numerical dating, has been often called absolute dating, which is very confusing. I think it's a very misleading term. It seems to imply that it's really, really precise. No, numerical dating may or may be more precise. Some methods may be more precise than others, but that's not what we're talking about. Okay. What we're talking about is placing dates on a timeline. And all those dates are going to have an error bar. Okay. So it's not saying this is the absolute date it happened on exactly that year. Okay. It's saying we can put a date on the timeline and it may be an approximate date and it has a certain error bar. And any time that such research is reported, it always includes what the error bars are. So absolute dating, or I much prefer numerical dating, determines when something lived or when a particular event happened in Earth history, putting dates on the timeline of Earth history. And again, it has a range of error. To put a date on a geologic unit, you need a clock. And you need a clock that runs at a constant rate. You can't have a clock that keeps changing its speed. Okay, it has to run at a constant rate, and it has to run at a constant rate regardless of environmental or physical conditions. Well, obviously, early on, it's just the beginning of working out Earth history. There's obviously the interest in, well, how old really is this, right? And particularly, how old is the Earth? And so there are a whole number of different ways that people try to get at that. And I'm just going to give you a few of them just to show you the kinds of things that were tried and why they don't work and why they fail. Um, One of the first ones was sediment accumulation. A person called Charles Walcott attempted to determine what the sum total thickness of all the deposited sediment was um, in an area and even globally. And then basically assume a certain rate of sediment accumulation based on modern observations and coming up with some number. Uh, and so you have a thickness, and then you have an estimated rate, and that gives you a date, right? And so he came up with numbers somewhere between 35 and 80 million years. Problem with that is that sediment accumulation is not constant, and different types of sediment deposition have vastly different rates of deposition. So this does not work. Another person tried the salinity of the oceans, a person called John Joly. And so he tried to say, okay, let's assume that when the oceans first formed, they were fresh water. So that means I need to calculate how quickly salts have been added to the ocean. And so we could go all the way around the world and measure the salt content of all the rivers flowing into the ocean and say, okay, combining all this data, the rate of salt influx into the oceans is so much. And he knows how salty the ocean is. So how long would it take for the oceans to reach that salinity? And he arrived at a wide range of dates from 90 to 150 million years. Well, again, the problem here is that one, these rates aren't constant, and also the ocean is currently in a steady state. That means that the amount of salt or any given compound that's dissolved in the ocean water, the rate at which it's added to the ocean is the same rate at which it's removed by sedimentation and other methods. So basically, the chemical composition of the ocean is quite stable because it's been in existence for a very long time and it's reached this uh, stability of inflow equaling outflow. So again, this doesn't work. Very, very famous one, Lord Kelvin, who was a very, very highly respected physicist, the turn of the century, determined that the Earth was probably molten when it formed and very hot. And so we know what the temperature of the Earth is now, and there's what's called a geothermal gradient, how quickly the temperature rises as you go as you go deeper in the Earth. And he used that to calculate how quickly heat was escaping from the Earth. So again, he has a rate, that's the rate of cooling, and what the current temperature of the Earth is. Okay, how long would it take the Earth to cool down to that? And again, he came to a really wide range of dates over his lifetime, varying from 400 million years to 20 million years. But again, there's a number of completely erroneous assumptions involved. One is the method of cooling, how hot the Earth was originally, how accurate the geothermal gradient was, and there's so many things here that aren't constant or there's no control for. He did the same thing with the sun. This is interesting because at this time they didn't know what heated the sun. And he assumed that the sun's heat was simply a result of gravitational collapse and gravitational heating. And so, okay, how long would it, how long would it take the sun to cool off, right? Again, it's very, very hot at its formation because of all this gravitational energy. Now that's being dissipated. So how old is the sun, basically? And again, this incredibly wide range of 10 to 500 million years. Well, as you can see, these methods don't work. They also don't result in any very um, narrow age determination, these wide ranges. And again, what they don't have is a constant rate. They don't have a clock. None of these things are adequate clocks. They don't run at a constant rate. In comes the discovery of radioactivity. So in 1896, Becquerel discovers that uranium salts emit some kind of invisible radiation. Shortly after that, the very famous husband and wife team of Marie and Pierre Curie discovered that thorium emitted radiation, and they gave that the name to that radiation, radioactivity. So they coined the term. And then subsequently to them, Rutherford and Soddy discovered radioactive decay. In other words, certain elements that are emitting these various types of radiation are unstable, and they spontaneously decay into stable or non-radioactive daughter elements. And it turns out that this occurs at a very steady, constant rate. Here's a picture of Marie and Pierre Curie. And so radioactive isotopes provide a constant clock. And this has been considered, there's been all kinds of tests done to confirm the constant rates of radioactive decay, and all experiments and all observations conclude that these rates are absolutely constant. And they are unaffected by physical conditions. So now we have a clock, and clocks that can run for a very, very long time. And so we finally have something that we can use to date rocks, even those of a very vast age. So just a couple very quick introductions to radioactivity and radiometric dating methods. If you're more interested in this, there's plenty of information out there to follow up in more detail. So first, you need to know what an isotope is. An isotope is isotopes are atoms with the same atomic number, that is the same number of protons, that's what the atomic number is, but different mass numbers. The reason what gives an atom most of its mass, nearly all of its mass, are the numbers of protons and the number of neutrons, which are about the same mass. For a given element, the atomic number is going to be the same. So the number of protons is going to be the same. But there will be, in many cases, different numbers of neutrons. That will make those different isotopes have different weights, different masses, even though they're the same element. So here's some examples of strontium-86 and strontium-87. Both strontium, one is one proton heavier than the other, or lead-206 and lead-207. Okay, so how does this work? Some isotopes are not stable. These are called radioactive isotopes, and they spontaneously decay. And often with a series of steps, some cases just one, but often it's multiple steps from the radioactive isotope. It may decay to a couple other radioactive isotopes, but eventually it decays to what's called a daughter isotope, which is stable and is not radioactive. And the rate at which this happens is constant. There are several different kinds of radioactive decay. There's beta decay, in which a neutron breaks into a proton and electron, and the electron is ejected from the nucleus. So a neutron turns into a proton, which means the mass, the weight of the atom stays the same, but its charge changes, which means its elemental name changes. In alpha decay, a nucleus fragments and a helium nucleus is ejected. And in electron capture, an electron falls into the nucleus and combines with a proton and creates a neutron. Okay, so again, that's changing the charge. So let's look at an example of beta decay. So this is the rubidium strontium radioactive decay series. So it goes from rubidium 87 to strontium 87. Notice the mass is the same, but the charge has changed. So with the diagram there on the left, that's the rubidium 87. And you see in the center there is a neutron, the gray sphere, right? So it undergoes decay. In the process, it ejects an electron. So it was originally it was originally a neutron. So it ejects an electron, that makes it positive. So it changes from a neutron to a proton. And that changes it from rubidium to strontium. So that's an example of beta decay. So I said that radioactive decay occurs at a constant rate. That constant rate is called a half-life. And what a half-life is it's the time that it takes for half of the radioactive atoms in a sample to decay. Okay? The time takes for half of whatever number of atoms there are at a given time for half of those to decay to a stable daughter. Every radioactive isotope has its own characteristic half-life. Some are extremely short, some are just fractions of a second, and others are literally billions of years. So there's a huge range in what the half-life is. So here is a simple diagram of how half-lives work. So you start here with a parent, and for real simplicity, let's say that it has 16 atoms. So you have 16 atoms, or 16,000 or 16 million or 16 billion atoms of the parent, of the radioactive parent, right? In one half-life, half of those 16 million turn into a daughter. So in one half-life now, the parent will have 8 billion now, half what it was, but now there's 8 billion daughters. In another half-life, half of those 8 billion decay. So now you have 4 billion. But now you have 4 billion more daughters, right? So now you have 12 billion daughters and 4 billion parents, and so forth, until you essentially go to zero. Okay? So that's how half-lives work. So as the parent decays, the number of parent atoms decreases, and the number of daughter atoms increases by that same amount. So here's a list of some very common decay series that are used in dating. And by the way, very, very shortly after radioactivity was discovered and radioactive decay was discovered, it was immediately thought, we can date things with this. And so they started very, very early in coming up with methods used to do radioactive dating, radiometric dating. So there's carbon nitrogen. So this is the well-known carbon 14 dating method, the half-lives for that decay series is 5,730 years. Oftentimes, when people talk about radioactive decay or radioactive dating, they immediately refer to carbon dating as if that's the only kind of dating that exists. And carbon dating has one of the shortest half-lives of a useful decay series. And so it's only really useful for dating fairly young things, like archaeological sites and anthropological sites. It's only good up to maybe 20,000 years or so. So you can't go back very far. Uranium lead has a half-life of 704 million years. Potassium argon, 1.25 billion years. Another uranium, that's U-238 to lead-206, has a half-life of almost 4.5 billion years. And rubidium strontium these are half-lives, have a half-life of over 48 billion years. It takes 48 billion years for half of the original rubidium to decay. What that means is you have this wide range of tools that can measure everything from things that are happening, um, in physical anthropology to things that can date the age of the universe, and the age of planets, the age of the Earth. Different radioactive isotopes can be used to date only certain types of minerals and rocks. In other words, you can't just pick up any old rock and say, oh, I'm going to date this using uranium lead. You have to have the right kinds of minerals that are capturing those radioactive elements and or stable daughter products. So you have to have a crystal, a mineral, that when it's formed, essentially makes a cage around those radioactive elements and keeps them from being lost. Okay? So you have only use certain minerals or certain compounds are datable, and you have to be sure that they haven't been modified, they haven't been reheated, they haven't been affected in some way that would cause some of the original, either the radioactive parent or the stable daughter, to be lost, in which case your numbers don't mean anything. So takes a lot of very close analysis, a lot of care. So what we need to know are the original amount of parent isotopes that were present or the original amount of daughter present. Don't need to know both, but you need to know either how many parent isotopes were originally present or how much daughter was originally present. You need to know the half-life of the isotope, and you need to know the amount of stable daughter isotope produced or the amount of parent remaining. So that's what you need to know in order to calculate a date. So we'll just look at a couple dating methods. So how do we know, how do we get at those numbers that we need to know? Like, how do we get to know what the initial amount of the isotopes were in the mineral to start with? Well, it depends on the type of dating method you use. If you use the potassium argon method, argon is an inert gas. So the radioactive potassium-40 decays into argon-40. Argon is inert gas or a noble gas, which means that it doesn't chemically combine with other things. It's extremely stable and it doesn't react to things. As a result, the argon is not present in the mineral when it first crystallizes. Because it won't combine in the mineral. So all the argon-40 that's present in a crystal was produced by the radioactive decay of the potassium-40. So again, the mineral now acts as a cage, and any argon that's produced is trapped within that crystal and can't get out. But until that crystal forms and creates that cage, the argon will just escape. So we know that the amount of argon at the beginning was zero. There are a few common minerals that contain uranium. So this is for uranium lead methods. One of those is called zircon. Zircon is a very good mineral, very good crystal to date. Um, it does a really good, it's very stable, it lasts a long time. Uh, so it can date, if you have very old rocks that have zircon in them, um, zircon is a very good mineral to date. Zircon is exceedingly low in initial lead. So again, kind of similar to the previous one with the potassium argon, there's very little initial lead in a zircon crystal. So again, the amount of initial lead can basically be determined to be zero. It's effectively zero. Then there's a very different method that's called the isochron method. This is a little bit trickier. And I'll just say a few things. This is rubidium strontium. Um, when a crystal forms, a mineral crystal forms, it can't tell the difference between strontium 87 and strontium 86. Okay. And strontium 87 is the daughter product. It's produced by radioactive decay, but it can't tell the difference between those two isotopes. So when the mineral crystallizes, it will incorporate whatever strontium is around in the environment in the proportions of those isotopes. It doesn't change the concentration or proportion of those strontium isotopes as it can't tell the difference. So if you make a plot of rubidium, which is the radioactive parent, against against the stable strontium, and the daughter, stable daughter, which is strontium 87, against the common stable strontium 86, you don't need to know the amount of initial radiogenically produced strontium 87. So that all the minerals, so you have a lot of different minerals that are all crystallizing in at the same time as this rock is forming. So rock is composed of lots of different minerals. And all those minerals, when they crystallize out, will have the same initial ratios because they'll just uh, take in the proportions that are present in that environment. So what happens is over time, if you plot um, the rubidium 87 against the stable strontium and strontium 87 against 86 in a plot, the plot results in a straight line. And it turns out the slope of the line indicates the age of the rock. So that's, again, just briefly. So the line at the bottom there, that red line at the bottom, represents a number of different minerals in the same rock. So all those minerals formed at the same time, but they're different minerals. But they all crystallize out with the same ratio of strontium 87 and 86. Okay. So the same ratio of the decay product to strontium-86. So that's why that's a straight line. They all had the same initial composition. But over time, what happens is the rubidium changes to strontium-87. So if you take one of those dots, okay, so after a certain amount of time, uh, the rubidium 87 will decay. So that rubidium 87 number gets smaller. So the ratio, so the ratio of strontium 87, rubidium 87 to strontium 86 goes down. So the line goes to the left. And the amount of strontium 87 goes up by the same amount. So the one ratio drops and the other ratio increases by the same amount. That results in at any point in the history, all those concentrations will always line up to form a straight line. And the older the rock is, the more 87 is decayed, the more strontium 80, the more rubidium is decayed, and the more strontium 87 is produced. And that line continually has a higher and higher slope. And that slope, how steep the line is, tells you how old the rock is. This is actually an example of that. This is a famous meteorite, the Tayshit's meteorite, dated by this method. And notice all the points line up. That's not fake. That's actual how the data comes out. That tells you this is a very good specimen. Since the numbers always line up in a perfectly straight line. And the slope of that line says that that meteorite was 4.52 billion years old. Okay, so what do these numbers tell us using these various radiometric dating methods? The date of the oldest rock that we know of on Earth is 4.03 billion years, a little over 4 billion years old. The oldest mineral grain yet found on Earth is a little over 4.4 billion years old. You're saying, "No, wait a minute, how can you have a mineral grain that's older than the rock?" Well, actually, mineral grains are always older than the rock. Um, So, think of just as a simple example, you have sand grains in a sedimentary rock. So you send a sandstone, in the sand grains in a sandstone. Well, that sandstone has a certain age of when it was formed, but the sand grains that make up that rock pre-existed the sandstone. So the sand grains are older than the sandstone. The oldest meteorites are about 4.55 billion years old. The oldest moon rocks are about 4.59 billion years old. Um, so a couple closing remarks here about using radiometric dating. Radiometric dates are confirmed by using multiple methods on the same samples, if at all possible. This is very common in science in general. You want multiple independent methods of getting at the same information, the same numbers. So in many cases, a given rock will allow you to use more than one method. And those methods should give you the same number. And if they don't, something's wrong. And you go back and check and find out what was methodologically wrong, just experimentally wrong, whether the rock was contaminated or whatever. But you want to see the numbers agree. Absolute dating has confirmed the order of events already determined by relative dating. So remember, relative dating is just putting things in order, putting them, this came first, this happened, then this happened, then this happened, then this happened, then this happened. So we already knew the order of events roughly from relative dating. Radiometric dating comes along and actually allows you to put actual numbers on that. And the numbers are consistent with that relative order. So it confirms the relative dating that was done earlier. As we said, only certain rocks and minerals can be dated radiometrically. You can't just go pick up a random rock and date it. Igneous rocks and volcanic ash deposits are particularly good for dating. The dates obtained by radiometric dating are used to put limits on the ages of other rock strata using principles of relative dating. So again, I have another hands-on video where I work this through, where I give you a geologic cross-section and I show how the relative dating and then producing numerical dates and showing how you can say this series of rocks is younger than this date and older than this date. So that's what radiometric dating does. And it places dates in the geologic timescale. So again, this is something I do in that other video. I'm not going to spend time working through it here, but you have the relative dating of just the sequence of layers, the order in which they formed, and then there are certain datable units, volcanic ash layers, basalt, which is a volcanic rock, and intrusion, that vertical line, which is a igneous intrusion, which again is datable. And that allows you then to bracket the ages of the intervening sediments and events. So let's conclude by just looking at geologic time with timeline with actual dates on it. One of the things about geology is the ages, the dates you use in geology is called deep time. But it's so different from the time that we're used to. And oftentimes it's very difficult for people to grasp it. The numbers are so big, the times are so long. It's very different, okay? And the term deep time has been coined, which is, I think, a good term. So the age of the Earth is about 4.5 billion years. The first evidence of life is about 3.5 billion years. So it's about 1 billion years before we have any concrete evidence of life on Earth. First multi-celled organisms, which were seaweeds, are about 1 billion years old. The first multi-celled animals, metazoans, first appear about 800 million years ago. So that's things like sponges. The first land vertebrates occur about 360 million years ago. Extinction of dinosaurs, we all know, is about 65 million years, datable by the Chicxulub impact crater in Yucatan. Our own genus, Homo, is something like 2.5 million years old. And our own species, Homo sapiens, first appears something like 500,000 years ago. So again, those numbers are hard to put your head around. So what I've done here is I've taken those same dates and I said, okay, let's just say the age of the Earth is 1 calendar year. So let's then put the beginning of the year, beginning of that clock, that 24-hour clock, this is a clock, a calendar, not a clock. The beginning of the calendar, January 1st. So the first evidence of life is March 21st. The first multicellular seaweeds are October 15. The first metazoans, the first multicellular animals, are late October, almost November, October 29th. The first land vertebrates, so the very first amphibians, December 2nd, last month of the year. Extinction of the dinosaurs, December 27th, only 4 days from the end of the year. Our genus, December 31st, the last day of the calendar year at 10:06 p.m. And finally, our own species, December 31st at 11:59, 1 minute before the end of the year. And that puts our lifetime and recent Earth history in perspective. So, hope this gives you at least a brief introduction to how we come about the numbers that we have for dating events in Earth history. And again, I encourage you to look at those other videos.